Okay, how's it going, guys? Welcome back. Today we are going to take a pause on learning any new material, and we're going to take a look at a few interesting free response questions from a couple of past exams. I'm actually just going to go over two of them, and the first one I just want to go over part A. The second one I will go through a little bit more in detail in terms of the other parts. But then I'm going to have you guys try two of them on your own that are somewhat similar. And the reason I want to focus on this is because it's a lot of what we've been doing on the other videos and in class. But there's one sort of unique piece to all of these that I think has a good chance of possibly popping up this year. And so that's something I want to focus on, number one. But then number two, it's I think they're just interesting problems, and they kind of wrap a lot of stuff together for us based off of what we've done already. And so just trying to converge, no pun intended, everything together here with everything we've done. And so I hope this video won't be nearly as long as the other ones. Okay. So I'm going to jump right into it. The first question I want to look at is from 2016. And I'm just going to look at part A here to sort of set up, the reasoning for why I'm picking the problems. Okay. And so you can see that this is definitely a Taylor series problem. We're talking about some function that we don't know, f of x. And what I know is that we're centering the series around x equals 1. Okay. So my C value is 1 throughout this problem. The reason why I wanted to show these problems is because pretty much starting right around 2016, the exam writers have become more and more creative with how they have you produce a Taylor series for a certain function. And again, in this case, we don't know what f of x is, but that's okay. We can still work with the Taylor series as if we did know what f of x was. The one thing I want to highlight, and I know I've said this before and I would work with this, but again, it's worth taking taking note of more and more as we go through, is this blue box, right? So I added this blue box here, and this is just our Taylor series, our general Taylor series construction form. And the piece I really want to focus on, because it's the piece that all of these problems have focused on recently, is the derivative part, right? So the f to the n of c, not c itself, but just this whole part right here, f to the n of c. The other parts you absolutely need to know. Okay. And in fact, f to the n of c divided by n factorial has also been these two parts together has also been a really important piece in past exams or past questions, because it is the coefficient of the Taylor series. So f to the n of c divided by n factorial. But these couple of questions that I have here more recently really just focused on the derivative, okay? And then using the derivative to put the whole thing together, okay? So you absolutely need to know this whole form, but the ways in which these questions ask you to find the certain derivatives, so the nth derivatives, have become more and more creative and potentially more and more difficult. And so I wanted to make us aware of that and just try a few. And I think they're just really good problems in general. They, like I said, they kind of mash a lot together, which is good. So jumping back into this problem. This one wasn't too bad. I'm going to show you the next one, 2017. It gets a little bit more difficult. And then I'm going to have you try 2019, which is probably the most interesting one so far. So here's what I know. Typically, you're given some information about derivatives, all right? And typically it has been the first and the 0th derivative, right? So the actual output of the function in the first derivative. So in this case, we know that f of 1 is 1 and f prime, or f to the first of 1, is negative 1/2. All right, so those are good. So I could actually create the first two terms of my Taylor series without doing any work, really, right? I just have to plug them into this form, plug n equals 0 and n equals 1 into here, and then I've got my first two terms. So that's actually really nice. It's a good start for us. However, from there, if I'm looking at part A, I know I need to write the first 4 non-zero terms. So I'm definitely going to have to figure out 2 more derivatives and then 2 more terms. it gets a little bit interesting here because I'm no longer given the derivatives just flat out like, hey, here it is. I have to actually find the derivatives. And you're given a formula in order to find the derivatives, specifically at x equals 1, which matches up with my center. So I'm good. And so throughout these problems, you'll be given something similar to this. All right, some formula or some way to produce derivatives in order to fill out the rest of your Taylor series general form. Okay. And so for this one, what we notice is that I have to now get the first four non-zero terms. I've already got the n equals 0 term, the n equals first term. I need the n equals second and the n equals third. So n equals 2, n equals 3. And so what I need to do is physically plug in n equals 2 and n equals 3 in to this form. All right. Once I do that, all I have is this f to the nth term, right? I need to then fill out the rest and make sure I put x minus 1 to the second divided by 2 factorial plus blah, 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 x minus 1 to the third divided by 3 factorial. And then I need to put that whole thing together, all right, including the first two terms that they already gave me. All right, so I'm going to jump to the answer just so we can see it all kind of written out here. Okay, so first term I was given, all right, so I know after the f of 1 equals 1, I was told that. I was told f prime of 1 equals negative 1/2. And then I actually have to find the second derivative and the third derivative at 1. Right, so again, I'm getting 1 over 2 squared and then negative 2 over 2 cubed. Go back to this piece right here that you were given and try it, right? So plug in n equals 2, you get negative 1 squared, which is positive 1. 2 minus 1 factorial is just 1 factorial, or 1 over 2 to the second. So there's 1 over 4. All right, so the second derivative at 1 should be 1/4. And then, so we'll just go back here really quickly. 1 over 2 squared, which is 1/4, so that works. And then if you plug in 3, we get negative 1 to the third, so that'll stay negative. 3 minus 1 factorial is 2 factorial divided by 2 to the third. So 2 factorial is 2. 2 to the third is 8. So you should get 2 over 8, or again, 1/4. So let's see that. I leave it as negative 2 divided by 2 to the third, which is fine. And in fact, this is a good chance to say now that if you're putting these pieces together on an exam or really whatever, it doesn't matter. If you don't want to simplify, you don't have to, which is nice. So you won't get points off for not simplifying. And so if you want to leave it just how you found it, that's fine. If you're confident with your simplification, go for it. But just be careful, because obviously that leads us to more mistakes. Okay. So again, once we find these, the derivative piece of the coefficient, we then want to plug it back into the whole formula itself, all right? Because we do want to find the first four non-zero terms of this actual series and then the general term for the series. So we'll have to use this again. Okay, and so we jump back here. I know it's going to start with 1. If you plug in n equals 0 to everything else, in fact, let me just grab this, put it on the screen, because I think that'll be helpful for us. So if you plug in n equals 0 and c equals 1 into this form, you should just get 1 itself. If you plug in n equals 1, we knew that first derivative was negative 1/2. X minus 1 to the first, there it is, divided by 1 factorial, so it just stays right here, 1/2 times x minus 1. And then I start using the rest, okay? So the first part of my coefficient is the second derivative. So 1 over 2 squared, that's this piece right here. And then I need to divide that, or in this case, I'll multiply the denominator by 2 factorial, which is just 2. Okay, and then over here, negative 2 divided by 2 to the third. They already simplified it for you. Technically, it'll be this term, so negative 2 divided by 2 to the third divided by 3 factorial. Okay, which in that case, the denominator, again, is just multiplied by 3 factorial. And so the 2 over 2 would cancel from that, right? That's really 2 over 6, or it would end up just being 1/3. All right, and then your general term, you were already given the derivative, which was, well, you can see the derivative, actually. What you're seeing is the pattern, right? So 2 to the 0, 2 to the first, 2 to the second, 2 to the third, and then that's always going to be multiplied by n itself. All right, and you can see that pattern to come out. You could simplify it if you'd like. You could take the derivative that you were given, and then it's just right here, so it's n minus 1 factorial. If you divide that by n factorial, then it would just be n on the bottom. So you could do that as well. You could physically take this, divide it by n factorial, and just do the like algebra and simplify it. Or you can notice the pattern either way. Okay. So again, that is just a creative way to get the Taylor series, at least pieces of it. And that trend has continued through a couple of different problems so far. All right. And so now I want to jump into 2017. Again, I'll focus on part A, and then I'll just kind of look through B, C, and D. B, C, and D are things that we've done before. All right. They're just good practice. And like I said, just kind of wrapping everything up. And then after I'm done 2017, I just want to highlight the 2 problems that you're going to do. And then the video's over. Okay. And so you can see right from the beginning for 2017, the setup is actually really similar, where we're given a initial output at a center value. So in this case, we're centering at 0 instead of 1. And then we're also given a first derivative at 0, which equals 1 itself. Okay. Let's see just what we have to do first, and then we'll get into exactly what the derivative piece here and how that's different than the last question. Okay, so we've got some function f. We have derivatives all orders for -1 to 1. Derivatives satisfying the Coulomb series converges for, so we know the convergence is -1 to 1. We'll show that the first 4, so we got to find 4 terms, non-zero terms. That's important for this question. And then they actually give us the 4 terms. So this one a little bit more interesting because they actually tell you what the answer should be. Your job is to just show that that is true, right? Show that you can get there. And so this is a little bit helpful, but I guess it could be frustrating if you weren't able to get to this piece. All right. But we'll see. It's not too bad. All right. And then we also have to find the general term. Okay. So let's look at this one. So we talked about the output. We talked about the first derivative. The derivative piece for the remaining derivatives is interesting because if you look at it, what I have is the next derivative. So the n plus first derivative is equal to -n. So whatever n I have to plug in here to get to my desired derivative. So the first thing I'd want to find is the second derivative. So in that case, n equals 1. I want to be careful there because your instinct is to plug in 2 because you're looking for the second derivative, but I need this to equal 2, right? So n has to equal 1 in that case. So n equals 1 for the second derivative. So that would be -1. And then the next part here is f to the nth. This is what's called a recursive, we can call this, in this case, it's a recursive derivative, but something called a recursive sequence. Basically what it does is it makes you look back to the previous term you just found or the previous piece of information. And so that's what this is doing, is it's taking the last derivative that was used or the last derivative that was found inside of the new derivative. So in this case, this is the f to the nth derivative of 0, or for the second derivative, since n equals 1, I have to look back to the first derivative. So I'm actually going to plug in the value of the first derivative in order to find the second derivative and multiply that by -n. All right. And so the second derivative itself should equal -1. And then you would go forward from there. You'd find the third derivative. So n equals 2. And then you'd actually have to go ahead and find the fourth derivative. So n equals 3. Why do you have to find 4 derivatives this time? Well, it's because it's the first 4 non-zero terms. And since the first term, the actual output was 0, that zeroes out the entire first term itself, right? So I need to then find 3 more additional terms or 3 more additional derivatives, because I've already given the first derivative, in order to find the next 3 terms itself, okay? And again, remember, finding just the derivatives isn't enough. I need to fill out this entire form, okay? So I'm just finding the derivative piece for the most part, and then I'm filling out the rest and simplifying if I have to. Okay, so if you went ahead and you actually started to find all of these derivatives, so we already found the second one, you would then plug in n equals 2, so it'd be -2 times the second derivative, which was -1, And so negative 2 times negative 1 should be positive 2. So that should be the third derivative at 0. And then you'd have to plug in n equals 3 to get the fourth derivative. So negative 3 times the third derivative, which we just said was positive 2, should equal negative 6. Okay, so I'm going to show this on the next screen. I'll actually pull up the answer. So here we go. Let's see if we were right. We were given f of 0 equals 0. We were given f prime of 1 equals 1. And then there we go. The second derivative equals negative 1 times the first derivative, which is negative 1. The third derivative equals negative 2 times the second derivative, and then so on and so forth. Okay, so it does look like we were right. And so again, just to notice this recursive piece, I'm using the previous derivative in the new derivative each time. Okay, excuse me. So now we have to take all of those derivatives and actually find the general term. I'm sorry, well, we do have to find the general term, but first we have to find the first 4 non-zero terms. Again, since the first term is 0, that doesn't count. I need to find 4 other terms. I was already given f prime of 1 equals 1. You plug in, the first derivative. In this case, c is 0, so it's always just going to be x to the nth. There's not going to be any subtraction there. So 1x minus 1x squared over 2 factorial. There's your minus 1, right? That's this guy right here. And then plus 2 divided by 3 factorial, x to the third, so on and so forth. And then they actually simplify it, okay? So if you plug in your derivatives and then fill out the rest of this form, you get this right here. All right. So I encourage you to, at any point, just pause the video and try and work it out yourself if you're not following with me here. And again, please jump on the video and ask me questions if need be. I'm happy to talk about this one for sure. Simplifying this one is important because you have to find the general term. Right. And again, could you find the general term by using the information you were given? Yes, but that's not exactly easy because, again, this derivative has a derivative inside of it. Like that's that recursive derivative idea. So finding a pattern or seeing a pattern here is actually really helpful. Now, luckily, the pattern's not too bad, right? And hopefully you kind of recognized it where the nth exponent is the same as the denominator, right? So the second x to the second divided by 2, x to the third divided by 3, x to the fourth divided by 4. I also noticed that it alternates. Now, what's a little bit tricky here is we were started with n equals 0, right? Because I know my first term is n equals 0. Unfortunately for us, that whole term zeroed out. So n equals 0 is your first term, which means you have to start your series at n equals 0. Okay, and so in order for it to alternate correctly, I know that my first non-zero term, so this x is positive, but this was your n equals 1 term. And so I have to start here with n equals 1, which means that this needs to be an n plus 1 in order for negative 1 to become positive. All right, and then you have your x to the nth divided by n after that. Hopefully you recognize this. This is a very important series for us, right? This is the alternating harmonic series. And that comes into play for the next question big time. All right, so that's the alternating harmonic. All right, let's just take a peek at part B here. So part B asks us to determine if the series converges absolutely or conditionally or diverges. And so we have to go through that process, right? And so remember what we talked about with absolute versus conditional convergence is the very first thing we did was, well, we took our series and we found the absolute value of it. And if the absolute value of that series converged, then it absolutely converged. And so specifically it asks us to find it at x equals 1. Well, if I plug in x equals 1 here, it's 1 forever, right? 1 to any power is just 1. And so I can actually simplify this entire series to just this, which is the exact harmonic series, right? Negative 1 to the n plus 1 over n itself. So if I take its absolute value, hopefully you realize there that it diverges because it becomes just the harmonic series. All right, and we know the harmonic series diverges. However, we've also learned that this is an alternating series. It decreases in magnitude to 0, meaning its limit goes to 0, right? And every other successive term is less. Therefore, it converges itself. And so if that happens where the absolute value does not converge, but the original series does converge, it converges conditionally. Okay, so have to put all those pieces together. Okay, let's move on to C and D. And again, we focused a lot on part A because that's really what this video is mostly about, but part C and D are good ones. Because part C puts together this idea of having to find an integral, right, which is something we just did. And so what we need to now find is the first four non-zero terms in the general term for the Maclaurin series for g of x equals the integral of f of t. Okay, so notice important that this 0 is the same center value that we started with, which is important because it's going to zero out every other term in this definite integral, right? That f of a is just going to be 0. And so really we're just finding the integral of f of x. Okay, and again, notice they're using t here just so those variables don't conflict with one another. All right, so just as a reminder, let's go back. This was our general term that we just found. And so really all we're doing now is taking this guy and integrating it, right? And so we're going to bump up the exponent by 1, divide by that same exponent, but keeping everything that we still have. All right, let's jump to the answer piece here. And so they have a lot of work here, right? And this is really showing you everything that you would technically have to go through. Okay, so this is actually raising each term, each of the 4 terms by 1 with the exponent and then dividing it by, the n plus 1. So it's actually plugging in the whole thing. Why? Because, well, it does ask you for the first 4 non-zero terms and the general term. So they're showing you how to get from one to the next for each successive step here. All right. For us, again, we know that there's 2 different ways. If you wanted to start with just integrating the general term, right, which is right here, if you wanted to just start with integrating this and then just plug in n equals 1, 2, 3, 4, whatever it might be, you can do that. But it might also just be as easy as, well, I've already got my 4 terms, so I'm just going to integrate them because that's just the power rule, and I know how to do that really easily. And then I'll just bump up the general term by 1 as well, okay? So they actually show the definite integral piece here. Notice that you don't actually have to do all of this work. You do need to show this because you need to show what your answer is representing. But really, this last line is the big piece that you need to show, okay? So you need to find, show the first basically 4 terms and then the general term. And you can do that just by taking what we had found previously, which is right here, and then right here, this general term, and just integrating all of it, right? So you could integrate each of these pieces individually and get your answer, and you'd be fine, okay? So what I encourage you to do is go back, take a look at this guy, notice that when you integrate these 4 terms and this general term, you do get to this answer right here, okay? And the general term, you could try and find a pattern here if you want, but you don't have to, because if you have this general term already, we're just going to n plus 1 divided by n plus 1. Notice that n stays, right? Because it's already there. It doesn't get replaced by n plus 1. It stays with it. All right. And then the last question, here's our error question. And so this is something that we literally just finished. And so hopefully you're feeling good about that. There's an nth degree Taylor polynomial. How do I know I'm talking about a Taylor polynomial now? Well, I've got this notation, right? P sub n of 1/2 represents the nth degree Taylor polynomial for g about x equals 0. So I'm using the center, which I know I have, but I'm evaluating it at x equals 1/2. So that's my input that I want to get an approximate output for. All right. What I need to show is that since this is an alternating series, which we talked about, the alternating harmonic, I need to show that the error for 1/2 is less than 1/500. Okay, and we actually just did this. And so we're going to use 1/2. We're not actually finding the approximation. We're only talking about the error, right? And so I need to show that P sub 4. So the key part here is that I'm using a 4th degree Taylor polynomial to approximate g of 1/2, which means that the error is going to be found using the 5th degree term, right? Not the 5th degree Taylor polynomial, just the 5th degree term itself. And so let's jump over to the answer here, just looking at this part here. And it goes through this, right? The first unused term, this question is really nice to you because it actually kind of connects things that you need to use prior, right? So it had you find the fifth degree term here for g of x, because they knew that you were going to have to use it in the error itself. All right, so the approximation only would have gone up to the fourth degree, but the error itself uses the fifth degree. So this x to the fifth over 20 is what I'm actually going to use to find that error, right? I have to actually plug in 1/2 into the fifth term. It's an absolute value, so this negative really doesn't matter. And so 1/2 to the fifth is 1 over 32. I would divide that by 20. It really just becomes 1 over 32 times 20, which is 1 over 640, right? Which is definitely less than 500. And so I'm good. All right. Okay. So hopefully that made some sense. Again, please let me know if you have questions. Part A was the big part I was focusing on in terms of creating polynomials. Creating Taylor series, terms of Taylor series, general terms of Taylor series. But the rest is also really good because it goes through basically everything, almost everything we've done with Taylor series so far. All right. All right. Let's look at the two that I want you to try. I'm not actually going to do these, but these are the ones that are for homework. So this was from last year. This has been the most creative way that I've seen students have to create Taylor polynomials or terms of Taylor polynomials, because it mixes in a little bit of, your very basic, at this point, differentiation theory. And this is from last year. This is a very kind of like A-B mindset where I'm actually given a number of nth degree derivatives. So I'm giving the second derivative, I'm given the third derivative, I'm given the fourth derivative evaluated at 0. So I'm using another Maclaurin series here. So that part's actually pretty nice because it gives you all this information. However, what it doesn't give you, which is opposite than the last two problems, is the initial output and the first derivative. All it does is it gives you the actual graph of f and then the line tangent to f at x equals 0. And so you have to use your knowledge of what all of that means in order to find the first term and the n equals first term, okay? Okay, sorry. So from there, I'm just checking. I thought I stopped recording and I didn't. Okay, good. So I'm going to leave you to that. All right, that was just sort of my my highlight there for you. The rest of it is also very good. Part B deals with having to multiply an e to the x function, which again we know by the function that you just created. And then part C and D. Part C is another integral that you have to find. This one's a little bit different because they're actually asking you to approximate it at 1. So you have to find the derivative function and then plug in 1, and then there's an error for that value for part D. And then finally, I want you to try 2009. So these are 10 years apart, but these are also really good. 2009 is a really interesting problem. I actually consider this more a differential equation problem. Obviously, it starts off with that, but we know differential equations, meaning derivatives, Taylor series and Taylor polynomials have a lot to do with derivatives. They're built off of derivatives. And so this question mashes these two ideas together. I actually think this would be a really good problem for the type of question you might have this year, considering everything that was cut out of the AP exam. It deals with Taylor approximation using a polynomial, and it deals with differential equations, which is free game. Okay, it uses Euler's method in the first part. The last part uses a particular solution, which again you might have to do. This is really good practice doing that. And then for part B, again, this sort of just randomly throws in finding a second degree Taylor polynomial for f about x equals -1. All right, and this is actually part B is actually really similar to part A of the last three problems that we just talked about, because again, it's another creative way in which you have to find a Taylor polynomial. Okay, and so I apologize. I'm going to actually correct myself. I said 2016 was one of the first times that they use, this idea of finding it. This is probably the earliest one. At least I could probably find more, but this is probably as early as we need to go back in terms of finding creative ways to make up Taylor polynomials. All right. So again, remember dy dx, that's the first derivative. D squared y over dx squared, that's the second derivative. And then it basically makes you or forces you to create the Taylor polynomial from there. All right. So give those a shot. I'll post these questions, the full questions, on my Malvern as well. You also have this slideshow that you can work off of. All right. Let me know if you have questions. We're going to cut it there. Have a great day and talk to you soon.